Thank you all for coming to hear about cubic surfaces of Markov type. And thanks to the organizers for inviting me, but also for a sustained effort organizing this seminar for several years already. It's been a great way to keep up with developments in number theory, and it's meant a lot to me personally just to hear friendly voices from week to week. So thank you very much. I don't see the full force of Zoom on my screen, but if anyone wants to do a Zoom clap for Philippe, Alina, and Mike, I think we all appreciate them very much. Thank you. I heard somebody clap. So the Markov cubic surface is sum of squares equals 3 times product. There's a solution 1, 1, 1. And it's a cubic equation because of the product, but it's really only quadratic in each variable separately. So you can change x to 3 times the product of the other two minus x, and you get another solution. So you can change 1, 1, 1 to 2, 1, 1, or any permutation of that. And then you can change either of the ones to a 5. And then you could change 1 to 3 times 2 times 5 minus 1, so that's 29. Or you could change 2 to 3 times 5 times 1 minus 2, so that's 13. So you keep applying these moves and you get more and more solutions that seem to grow larger and larger, arranged in a tree. So here is a picture by Don Zagier that I like very much because he drew the tree as if it's blowing in the wind. This is not so easy to do even today, and he did it in 1982. I'll say more about this paper in a moment, but here's the tree in a bigger font again. Sum of squares equals 3 times product, 1, 1, 1, and then a whole slew of other solutions. So my plan for this talk is to introduce you to the Markov equation if you haven't seen it before, or to review it if you have. In particular, there's some work of Will Chen, and there's a new proof just from earlier this year by Daniel Martin. And hopefully, if there's time at the end, I can tell you about joint work with Matt Litman and Yuma Mizuno, where we adapt Martin's proof to other cubic surfaces, where you change the quadratic form by adding some off-diagonal terms, and then you change the 3 to a suitable constant. So analogous trees of solutions were studied by Gyoda and Matsushita, and our interest is in how these reduce modulo p. Any questions about the plan? I assume not. In case we run out of time, let me state a theorem. Again, this is joint with Matt Litman and Yuma Mizuno, both from University College Dublin. We assume P is a prime, and we exclude 2 and 3. The parameters A1, A2, A3, mod P, should be such that AI squared minus 4 are quadratic non-residues, and S, 3 plus the sum, is not 0, mod P. I'll say more about that assumption later. So we consider the surface sum of squares plus off-diagonal terms equals S times product. S is not 0, so this is an honest cubic. And just like with the Markov equation, it's really only quadratic, so you can change one coordinate at a time by a move I call mi, where the indices I are taken mod 3. So the move changes xi to s times the product of the other two minus xi minus a new contribution from the off-diagonal terms. So that's a group action on some surface mod p, and the conclusion of the theorem is that all the orbit sizes are divisible by p, except 0, 0, 0 is a solution in its own orbit, and that has size 1, which is not divisible by p. So the Markov case is when you set all 3 parameters equal to 0. So in that case, this divisibility result is due to Chen. And Martin gave a new proof in the last couple of months, which is what we're generalizing. I hope it'll be clear by the end of the talk, once I say a little bit about the two proofs, that these are complementary proofs. They're very different from each other. They teach us different things about the Markov surface. It's great that we have two different proofs of the result. Chen's proof is sort of based on a character variety interpretation of the Markov surface. Martin's proof looks elementary, but I think it's secretly about cluster algebras. So they come from totally different perspectives. I see something in the chat. What is the meaning of quadratic non-residue? So quadratic residue would be like a square mod p. Quadratic non-residue means it's not a square, but it's also not zero mod p. That's the theorem, and hopefully by the end of the talk, I can sketch a proof and explain why we make these assumptions. So welcome to the Markov surface. You might be wondering which Markov and why do we spell it with two Fs? So there are three well-known mathematicians named Markov. The one I'm referring to is the father and the brother of the other two. He's the same one who's well known for Markov chains, but when he published on this subject, he spelled his name with two Fs. So we use the same spelling, and as a bonus, it makes all of the work on Markov mod p show up in searches as something different from Markov chains, which is good, and it makes it easier to find people from our community that you can read more about Markov at the link here. So Markov wrote two memoirs on this in 1879 and 1880. The first part of the theorem is that all integer solutions to the Markov equation, sum of squares equals 3 times product, other than 0, 0, 0, they're all obtained from four trees, repeatedly applying these moves where you start from 1, 1, 1 and build the tree, or you could start from a double sign change of 1, 1, 1. So you get four infinite trees of integer solutions. So if you only care about the positive integer solutions, then they all come from a single one of these four trees. The Markov numbers are just any coordinate of a Markov triple. So 1, 2, 5, 13, 29, those are all Markov numbers. And Markov made the first of many connections between these Markov numbers and other things in mathematics. So the questions he studied were oddly approximable numbers, like which real numbers are the hardest to approximate by rational numbers, and indefinite binary quadratic forms. So you could ask what the minimum of the form is, and Markov showed that there's a whole sequence of worst offenders. So more precisely, if you take triples with maximum equal to m, those correspond to classes under integer change of variable of quadratic surds and indefinite forms. So if you have a real alpha, you want to ask whether there are infinitely many fractions p over q approximating it up to accuracy q to the minus 2 times some constant, and that constant tells you how badly or well approximable the number is, and Markov numbers show up in that constant under this change of variable, 9 minus 4m to the minus 2 to the minus half. And that's the same number that equals the minimum of a corresponding form. So Markov explained how these are related to each other. So 9 minus something to the minus half, that's going to be at least a third. There's a very interesting story that continues below a third, but above a third is sort of the discrete part of the story that's parameterized by Markov numbers. So Markov found some very interesting ways they show up, and since then they've come up again and again in lots of different interesting ways. We know how many Markov numbers there are up to a given height. If you count ordered triples, x, y, z, up to some height h, satisfying the Markov equation, that grows like a constant times log h squared. So it's a pretty sparse sequence. And number theorists want to know, are there infinitely many prime numbers in this sparse sequence? That's open. It's even open whether there are infinitely many square-free. It's a very interesting question, how the Markov numbers factor. So here on the right, I've written the first several Markov numbers, and there's a check mark next to the primes. But so it turns out there's a restriction. They don't just factorize the same way as any numbers. Frobenius followed up on Markov's work and showed that all the odd prime factors of a Markov number are 1 mod 4. For primes that are 3 mod 4, there's also a missing residue class. The Markov number m can't be plus or minus 2/3 mod p for p congruent to 3 mod 4. If p is equal to 3, then m's not congruent to infinity. So here you've got the first several Markov numbers, and you can see how they factor into possible factors of 2, but then all the odd factors are 1 mod 4. So this is not hard to prove. If p divides a Markov number m, that means xy0 up to a permutation solves the Markov equation. But with a coordinate equal to 0, you just get x squared plus y squared equals 0. So either all the coordinates are 0, which is kind of ruled out from the beginning. Otherwise, you can divide by either one of the variables and get a square root of -1. So this can only happen if p is 1 mod 4. And in the same way, if you substitute 2/3 for one of the coordinates, you're going to get a square root of -1. So this is the basic obstruction. I see some questions. Yes. Yeah, so the Fibonacci numbers come up in an interesting way. You get every second Fibonacci number, like 2, 5, 8, 13 there. You get every other one. So the recent development in this subject is strong approximation. All solutions mod p lift to integer solutions. This was conjectured by Arthur Berger in his thesis. It's now known for all but finitely many p, and quantitatively, it's enough for p to have a few hundred digits for these methods to kick in. So that's been published earlier this year by Eddy, Fuchs, Litman, Martin, and Tripenny. An equivalent way to state strong approximation is that there are no congruence obstructions to being a Markov number, except the ones that Frobenius already noted, that they can't be 0 or 2/3 modulo primes that are 3 mod 4. So yet another formulation is that the Markov moves act transitively. So let x star of fp be all the non-zero solutions mod p. Strong approximation says that there's only one orbit under the Markov moves. So if you form a graph whose vertices are triples x, y, z, and the edges join a triple to its 3 neighbors under the Markov moves, strong approximation says that's a connected graph. In other words, everything connects back to 1, 1, 1, the root solution, and if you follow the moves in reverse, you'll be able to lift any solution mod p to an integer solution. So that's several different ways to think about this strong approximation that's now known for all sufficiently large p. So here's the Markov graph for the prime 7. We know exactly how many vertices there are. It's p times p plus or minus 3. And this is again from Frobenius's result that if p is 3 mod 4, you're not allowed to use 0 or 2/3. So there are fewer possibilities, and you only get p minus 3 instead of p plus 3. So that makes 7 actually the smallest example. It's fewer vertices than 5 because of this plus or minus that depends on p mod 4. So here 1, 1, 1 is the root solution. The tree kind of collapses as these cycles form. An interesting aspect of this is that over the integers, you would have sign changes. You would have also like -1, -1, 1. So mod 7, 6 is playing the role of -1. So you have four disjoint trees over the integers, which actually merge when you reduce mod p. So in this case, when p is 7, you can just draw the graph and check that you've got all the solutions. And strong approximation says that the same thing happens for all larger primes. You get one connected orbit containing all the solutions. No extra solutions mod p except the ones that come from integer solutions. So the proof of strong approximation comes from combining two separate parts of the argument. Bourgain, Gamburd, and Sarnak showed that if you take the non-zero solutions mod p, there's one large orbit that they call CP, the cage, which is large in the sense that as p grows, the complement is at most p to the little o of 1, smaller than any power of p. Chen, on the other hand, proved that any orbit has size divisible by p. So what's left after CP, either it's 0 or else it's going to be at least p because it's divisible by p. So once p is so large that p to the little o of 1 is less than p, CP is all there is. All the non-zero solutions come from one orbit, which is also the image of all of the integer solutions. So that's strong approximation. And reducing mod p allowed Bourgain, Gamburd, and Sarnak to prove a related result about how Markoff numbers factor. Almost all the Markoff numbers are composite. So that is certainly true in the ambient universe of all numbers. Most of them are composite. But if you restrict to a sparse subsequence, it's quite difficult to prove that all numbers are composite. So they were able to do that in the Markoff case by understanding what happens when you reduce mod p. This p to the little o of 1 in their result, that there's one big component and everything else is at most p to the little o of 1. P to the little o of 1 is a souped up divisor bound. It comes from divisors of p plus 1 and p minus 1. So a key part of their argument is to analyze what happens when you fix one coordinate and just do moves on the other two. So you start from x, y, z, you're trying to connect it to some other triple. Z stays the same throughout, and you just change x to 3yz minus x, and then you do a move on the second coordinate, and then you repeat that. So you just keep moving the first and second without changing the third. And the key point is that this is linear in x and y. The only nonlinearity comes from, taking products with z. So for fixed z, this is just changing x and y by a matrix of this shape. So if you do this L times, you'll just get the Lth power of a certain matrix. I see something in the chat. So you don't get to take complements for free here. If almost all Markoff numbers are composite, that's consistent with all of them, right? Yeah, there might be no prime Markoff numbers. I mean, we know there are some, but yeah, proving that almost all are composite doesn't say yes or no how many primes there are. Good question. The simplest thing that could happen is that you're trying to connect XYZ to another triple with the same third coordinate, and all you have to do is apply this matrix L times, and X and Y end up where you need them to go. That would be the simplest thing. The next thing, maybe Z is not the same all the way around, but you can fix the first coordinate by doing moves on the first and second, and then you get to some point here, but then you have to start doing the analogous thing on the second and third coordinates. And there's sort of a hierarchy here of having to switch more and more times to get farther in the graph. So the issue is that you might need to switch repeatedly if this matrix has a small order. And the order of this matrix, in most cases, it's going to be some divisor of p minus 1 or p plus 1, unless it ends up being a unipotent matrix. So the factors of p plus or minus 1 play a key role in how far you can go with this strategy. So there have been some very interesting later papers by Bella, a different Chen, Fuchs, yeah, and also by Silverman, going further into the analysis of how you navigate its Markov graphs for a large prime. So here's the Markov graph for the prime 7 again. If you look at the points where the first coordinate is 1, there are 8 of them, and they all form a ring. You can just go all the way around this 8 cycle, and you get all of the triples with first coordinate 1. So that's a relatively high order. That makes it quite easy to connect things together. Whereas if you take the first coordinate equal to 2, you have a self edge here, and then just these 3, and you have to navigate quite some distance to connect those to the other 3 triples that have first coordinate equal to 2. So if you need a mental picture to keep in mind here, here are 2 very different highways. On the left, we have the Swindon magic roundabout in between Bristol and Oxford. This is a notorious example of circles within circles and having to switch many times to get where you're going. And on the right, we have the Bundesautobahn 7, which is just a straight shot from Austria to Denmark, with more or less no switching involved. So as you navigate the Markov graph, sometimes you can go straight there along just one path. Other times you have to switch many times. And I think the way they actually occur in the Markov graph in sort of unfavorable examples is that it's not just a highway going straight up and down. It's more like a long, winding road, kind of going all the way back and forth. And even if they actually do connect everything together, they still don't give you the shortest paths. I think we're missing some shortcuts kind of hiding on the back streets that you can take. So anyway, that's a picture to keep in mind. I think we need to unleash our inner roundabout to learn more about these graphs. So Bourgain, Gamburd, Sarnak showed that there's one large component. The rest of the argument is a lower bound for possible remaining orbits. And ideally, the lower bound should be so large that it contradicts this p to the little o of 1 that we already know from Bourgain, Gamburd, Sarnak. So there are 2 very different approaches. What Bourgain, Gamburd, Sarnak did, which was improved by Konyagin, Makarychev, Sparlinsky, and Vugin, is what I would call a real method. It counts how many triples you have, and you make sure you've got a large number of them in the usual Archimedean sense. Whereas what Chen did, and also in the new proof, this is more of a p-adic thing. You're proving a number is large by showing it's divisible by p, which also happens to be large. So I think it's good to remember the argument of Konyagin, Makarychev, Sparlinsky, and Vugin. They show that each orbit is of size at least log p to the 7 of 9. And the idea here is that not all 3 of the coordinates can be bad. In other words, if we fix one coordinate and just do 2 moves on the others, for at least one of the coordinates, you're going to be able to take a power L that grows like log p to the power 1/3. So this was also noted by Bourgain, Gamburd, Sarnak, and that's where they stopped. And they showed that every orbit has size at least log p to the 1/3. But you can improve that by noticing that at many points along the way, you can branch even further and get a path of a similar length. So you get more points, and when you put them all together, you increase the power of log p. So it doesn't give a large enough lower bound to contradict p to the little o of 1. Log p to any power would still be p to the little o of 1. So it doesn't immediately give strong approximation, but I think it's a useful argument that you would need to follow in order to do more quantitative stuff with these graphs. On the other hand, Chen shows that each orbit is of size 0 mod p, and the proof is totally different. It uses a moduli interpretation of the Markov surface, which I'll try to sketch. So the underlying fact from linear algebra is Fricke's identity for 2 by 2 matrices of determinant 1. If you have A and B in SL2, then their traces solve a cubic equation of the Markov type. If you let X be the trace of A, Y the trace of B, Z the trace of the product, and K the trace of the commutator plus 2, then it turns out that the sum of squares equals the product plus K. This is just a fact for any two matrices in SL2. So if you imagine the constant being 0, this is now a rescaling of the Markov equation. The basic solution is 3, 3, 3. Both sides would be 27 if the constant were 0. So you have to divide all of the coordinates by 3 to relate Fricke's identity to the original Markov with 3 times the product. What this shows is that the Markov surface is a character variety. You can map a free group on 2 generators into SL2 by sending the generators to whichever matrices you like, A and B. And the traces will be the same for any conjugate by the same G of both those matrices. So certainly the trace of A and the trace of B will be invariant under conjugation, but if you use the same G, it'll also cancel out in the product and the commutator. So the whole thing will be invariant by conjugation. So the Markov surface is the part of Hom from F2 to SL2 up to conjugation, where you fix the trace of the commutator to be minus 2 in order to make this constant K be 0. The next step in Chen's approach is to think of the free group as a fundamental group of some space. So you take a punctured torus. The free group is now denoted by pi. That'll be pi 1 of the punctured torus. So you identify the opposite sides according to A and B. And the commutator now goes sort of all the way around the puncture from A to B to A backwards to B backwards. So the Markov surface is the part of Hom from pi to SL2 up to conjugacy, where you fix the trace going around the puncture to be minus 2. And this has moduli. You don't have to use a square torus. You could use any sort of shaped box you like. So there's a degree of freedom here. You could choose any torus from M11, the moduli of genus 1 curves with 1 puncture. So this is how to think about the Markov surface to go into Chen's proof. And I really can't do it justice here. I can just give some hints. I'll give you a link to the paper at the end. The keywords to look for are non-abelian level structures or non-congruence modular curve. So in the usual level structures or modular curve, you would have like an elliptic curve covering itself with respect to some structure you've singled out. Chen studies something much more general, and it's much more general than Markov. It goes way beyond that. You can take G to be any finite group, For Markov, you take the group SL2 of a finite field, and then Fricke's identity is going to kick in. But Chen proves a congruence in much greater generality. You take MG to be a suitable moduli stack of admissible G covers of elliptic curves. There's some technicalities I won't go into here. They're not actually G covers, they're G structures. But the cartoon to keep in mind is that you have some curve covering an elliptic curve with G as covering transformations. Uh, so Chen computes the degree of a line bundle in two ways to get the congruence. Um, there's a forgetful map where you forget everything except the elliptic curve E. You forget the whole cover to just map this mg moduli into just the moduli of the elliptic curve itself. So I call F this forgetful map. And ultimately, from Fricke's identity, any orbit you start from in the Markov surface is going to be some kind of fiber over a given elliptic curve on like all the possible G covers over that elliptic curve. So Chen starts from the Hodge bundle on M11. So much more generally, for curves in general, like MGN, any genus G, any number of punctures, uh, the points in that moduli space are supposed to be like curves, and the fiber over that point will be like the vector space of all differentials on the corresponding curve. So that's a vector bundle. But if you take genus 1, it's only a one-dimensional space of differentials, so it's just a line bundle. So in the cartoon, you should imagine just dz, like a one form on the elliptic curve. So that's a line bundle on M11. Chen pulls that back to a line bundle on MG. So on the one hand, the degree of that is going to be the degree of F times the degree of the lambda you started from. But on the other hand, Chen shows that it's a 2p power. Yeah, this line bundle on MG is some other line bundle L tensored with itself 2p times, so that the degree is 2p times the degree of L. Comparing that to degree of F times degree of lambda um, shows that the degree of F is going to have to be divisible by p. We know what the degree of lambda is. It's 1 over 24. That's another thing about Chen's proof. Everything is a stack, so the degree might be a fraction. But anyway, Chen knows what it is, and he can also show that this degree of L is not going to cancel out the factor p here. It could be a fraction, but it's not 1 over p, so the degree of F is going to have to be divisible by p, and that tells you how many points there are in the underlying orbit. So that's just the cartoon version. I encourage you to read Chen's paper for the actual version. So he gets something for any finite group, and taking SL2 of a finite field, he gets something for any Markov surface plus k, like Markov polynomial equal to k, not just k equal to 0. But it's not necessarily a congruence to modulus p. So in Fricke's identity, the constant k is always commutator trace plus 2. So what you have to do is write the trace as the sum of the eigenvalues. And then Chen's method gives you a congruence. It ends up being to modulus some divisor of the order of these eigenvalues. The special feature of the original Markov is that when the trace is minus 2, that corresponds to a double eigenvalue, minus 1. So instead of a diagonalizable matrix, you get Jordan form for eigenvalue minus one. So it ends up having order 2p, which is related to the ramification 2p that Chen calculates. So Markov is kind of the most spectacular case where you get a congruence mod p, and p is large enough to complement the bound from Bourgain, Gamburd, Sarnak. For other values of k, you get congruences, but as p varies, the size of the modulus will just be the order of some number mod p. So that's Markov plus k, varying the level set. Another family of cubic surfaces is to vary the quadratic form. So if you just take Markov plus k, it's not clear what starting point to use instead of 333 or 111, depending on how you normalize. If the constant were 0, you could just take 333 here. But for other k, we don't know where to start. So Gaussian Sarnak studied Hasse failures. I think k equal to 46 is the first time there's a Hasse failure. There might not be any integer solutions, so it's really not clear where to start. If you take this other form of like extra off diagonal terms and you adjust the constant 3 to 3 plus the sum, by construction, 111 is now a solution. You get 3 plus a1 plus a2 plus a3 on both sides. So you certainly have solutions, but the moves are different depending on the parameters. So Gyota and Matsushita showed that if you start from non-negative integers AI, all the solutions in positive integers come from the basic solution and then the tree of iterated moves from there. So these are pretty closely related families, I would say. I mean, you could certainly put them together, like vary both the level set and the quadratic form. But even if you don't introduce any extra k, you're still kind of led to the Markov equation. If you write the quadratic form in terms of a matrix, then the determinant of that matrix is a Markov polynomial plus constant in the parameters AI. So the the Markov family in the parameters AI is going to tell you something about the singularities of these surfaces in the x variables. So there's a very singular case where all the parameters are minus one. So in that case, 3 plus a1, a2, a3, that's 0. So there's no cubic term. It's just a quadratic. But you're also on this locus where the determinant equals 0. So there's no cubic term. It's just a quadratic. And that quadratic splits into two linear pieces. So that's the most singular case. And not only is 0, 0, 0 a solution to setting this whole thing equal to 0, but you can take t for any t, and that'll be a triple fixed point. So in other words, it's not true that all the orbit sizes are divisible by p. You've got to exclude more cases if you want to make that statement. So that's why I assume in the theorem that this coefficient of the cubic is not 0. Otherwise, you might have to deal with more exceptions. So in the time left, I would like to sketch a proof. This is very close to Martin's proof in the case when all the coefficients AI are 0. Here's the theorem again, joint with Matt Litman and Yuma Mizuno. P at least 5, sum not equal to 0, AI squared minus 4 quadratic non-residues. I'll show you where that comes from. I don't think it's really necessary to assume that, but for convenience, we do. So then you take these same surfaces as Gyota and Matsushita, reduce mod p, and we claim that all the orbit sizes are divisible by p, except for the origin. So that's what we aim to do. Step one is a pointwise congruence. In other words, for any point x, a certain congruence holds, mod p. I'm going to assume none of the coordinates are zero. So then you can divide by x1, x2, x3 on both sides. Uh, so the sum over all indices, mod 3, xi over the product of the other two, plus ai over xi, that's just equal to s because I've divided both sides of the equation. On the other hand, you can double count this ai over xi. So instead of just counting like 1, 2, 3 for the indices, each I is going to occur twice as a neighbor of the other two. So instead of summing AI over XI, you can sum the other two, and you're just going to get each index twice. So that's how you can simplify the congruence in this way. 1 mod p is the same thing as 1 over s times the sum of I mod 3 of xi over the product of the other two plus the average of the two off diagonal terms. So what we're going to do with this is count mod p. Like to count something, you just add 1 for every term, but we're going to add 1 mod p in this expanded way. So step 2, let v be the number of triples in an orbit O. For simplicity, we're still assuming nothing vanishes, so we can divide by something that's not 0. So v is the sum of 1 over all x in the orbit, but 1 is also the same as 1 over s times the sum over all three indices. So if you change the sums, so you sum first over I, then over x and O as the inner sum, and clear denominators, you can write 2SV as a sum over all indices, sum over all triples. So step 2 is to do that inner sum over the orbit by pairing each x with mix, where I is chosen I, and you do it one at a time in the sum over all I. So that's step 2, and the simplification is going to be that when you pair them up, each pair basically contributes the same thing. It no longer depends on x. So yeah, v is the size, O is the orbit. We're trying to show v is 0 mod p. Step 1, 2SV is a certain sum, and in that sum, step 2 is to pair x with mix. So here I'm assuming we don't have a fixed point. Mix is not equal to x. For any such pair, you get 2s out of this sum. I can tell you in a second what to do about fixed points. So this is just some cancellation that happens from the way the moves are set up. If you change x to mix, you get the same thing in the other two coordinates, but xi changes to the other root of the quadratic, so minus xi plus s times the product minus some off-diagonal stuff. Yeah, so when you pair the two together, it exactly cancels to 2s. Roughly, you would have v over 2 pairs to make v. So that's going to cancel the 2. So 2sv from step 1 is the sum over all indices, sum over all pairs, 2s for each pair. So this is 3sv because there are v over 2 pairs. So at this point, something has to be 0. If 2sv equals 3sv, p is at least 5, so 2 and 3 are what they appear to be. There's no problem with those. Either s has to be 0 or v has to be 0, mod p. So we've assumed s is not 0, so that's how you deduce that v does have to be 0. So step 1 and step 2 together yield not exactly a theorem. There are several issues here. I've assumed that nothing vanishes, and I've assumed that there are no fixed points. So you have to deal with that somehow. So here's the proof just written out again on the left with the definition of the move. 2sv ends up being equal to 3sv. Um, yeah, so the first issue is easy to deal with. If x equals mix, that still counts as a pair, but instead of getting xi plus xi prime, you're only getting one term, xi, and the fixed point equation tells you what that term is. Also, the off-diagonal stuff, you only get once instead of getting it twice. So the upshot of this is that instead of 2s like you would get for a pair, a singleton only contributes s. So fixed points are no problem. Um, in particular, it doesn't matter whether v is even or odd, and there's still v over 2 pairs if you interpret singletons correctly. The reason we assume AI squared minus 4 is a non-residue is because I still don't know how to deal with the possibility that some coordinates could vanish. In Merton's proof for the Markoff case, he does deal with that. It turns out you can interpret this 2s as just s plus 0. If it looks like you're going to have to divide by 0, that there's a way to just interpret it correctly. Um, I haven't found that generalization yet for off-diagonal terms. So the thing is that if you set xi equal to 0, you get a conic for the other two coordinates, which reduces to a pair of lines. You can just solve it, and there aren't any solutions if the square root doesn't lie in the base field. So you can just avoid the problem by assuming that these are non-residues. In the Markoff case, this would be like Frobenius's obstruction. If AI is 0, this would just be like a square root of minus 4. So if there is no square root of minus 1, you don't have to worry about 0. For general parameters, you would have some more complicated congruence on P that allows you to avoid the 0. Anyway, so that's a sketch of the proof. Thanks very much for having me. To summarize things, we're looking at cubic surfaces of this form, like Markoff plus some off-diagonal terms. 1, 1, 1 is by construction always a solution, and you get a tree of solutions from there, ignoring, sort of special cases like all parameters equal to minus 1. When you reduce mod p, it's no longer trees. The cycles form. You get some other orbits, but for suitable parameters, all the orbit sizes are divisible by p. In the Markoff case, when all the parameters are 0, there is only one orbit, and it's definitely of size divisible by p. It's p times p plus or minus 3. So here are the Markoff numbers and their factors, and sometimes you get congruences between them. For example, like when 194 is congruent to 5 mod 7, that sort of explains this hexagon forming in the Markoff graph mod 7. If you start doing the Markoff tree, mod 7, you get two different paths to 13, 5, 5. So that closes up this hexagon. In the same way, 13 and 29, those are plus or minus 1 mod 7. So that's why you get these self edges forming. So I'll stop there. These slides, I think, will go up online, and then you can check some links to some of the papers I mentioned, including a preprint from Mirzakhani, where she counts Markoff triples up to a given height and actually does much more. It's a far-reaching generalization for mapping class groups.